Okay, can everybody see that?
Yes.
Okay, good. Of course, I've now lost. I hate this. Somehow I've lost all you guys too, so I can't really see you. I'm not an expert at Zoom, as you can tell. So, oh well, we'll just go with it. Sally, to answer your question, and I'm sure everybody, what they're referring to is kind of, let me see, this phenomenon. So here, for example, their models that they're doing are doing these various tasks. And as you can see, this is the size of the model here, the 10 to the 18th, 10 to the 20th, 10 to the 26th. So these are big already. And what they find is that as these models reach certain levels of size, their accuracy, for some reason, just shoots up dramatically. And this is on many, many tasks they'll go. You can read the various ones. Can everybody sort of read the various names of the tasks? Oh, here.
Yes, I could.
Yes, we can read it, yeah.
Okay, good. Just wanted to make sure. So you can see that right there. You can kind of see that some of these just really, really shoot up. And then they go through several other ones. Let's see here. And they talk about various prompting strategies they can do, but they still exhibit this accuracy, if you will, real ramp up on these like word problems and things like that. So the question is, why does this occur? Is this something we can exploit? And how do we predict, for example, when this emergence, using their term, is going to occur? Does that make sense? Okay, hopefully so. And I think they had gone through some of these. They talked about some prompting strategies to prompt in a way that would work best with these emergent technologies and various other things. This is kind of the key message I got from it. Is it possible if we continuing to scale up, language models in the future could have even more abilities? So that's kind of the key question they're asking. This is, as I said, these are Google people, and this is actually, I believe, a Google conference between various engineers at various Google locations. And then they started moving into various ways they had approached this. One was this chain of thought prompting. And let's see here if we can go on. And this was one paper that they referenced in there. And maybe this is kind of a good place to start right here, if you guys don't mind. It's a little bit, we're about 10 minutes behind where we were, so I apologize for the people that were here last week, but it's kind of important to kind of follow along this. So I'm just going to start here if nobody has any objections. Okay. And let me know if you can't hear or anything what they're saying.
If you wanted a model to answer any question about Wikipedia, then the model would have to be as large as like a compressed file that contains the information on Wikipedia, right? So there is something crucial.
Oh, one thing about our rules here too, nobody knows all this stuff. If you have a question, just unmute your mic and say, could you stop? Or I have a question or whatever, and we'll stop. We get as far as we get, and we just want to make sure that everybody gets something out of this, okay?
About scale, but it's possible that you could do it with less scale than we're doing now. Does that help? Or
Thank you.
okay, so I'll move on to talk about reasoning if there are no other questions for now. Great. So the second sort of part is going to be about sort of a set of work that our group has been working on around chain of thought prompting. And here's the paper. And before I dive in, I should say this work is done in collaboration with a lot of people who have been on the reasoning team here at Google, and on the right is sort of a screen cap of Sundar presenting a chain of thought prompting at our press event, and there's a link to video if you're interested in watching that later. So the motivation is that language models can do sort of a range of tasks well. So for instance, if you take, the typical sentiment analysis or machine translation tasks, language models can achieve very good performance in few shot or even zero shot scenarios. And one way of seeing this is that language models are very good at type 1 tasks, which are tasks that are done easily and maybe even subconsciously by humans. So basically, by the time you finish reading the sentence, you would have the answer to the task. And then on the other hand, there are type 2 tasks, which require deliberate thinking, often with multiple steps. So this includes different kinds of multi-step problems or logical reasoning tasks like the ones shown here. And language models often can't do these tasks correctly. And even if you increase the model scale, it doesn't really enable the performance to increase by a lot. Here's sort of an example of the method we're going to propose to solve this. So here there's sort of a multi-step math question. So Roger has 5 tennis balls. He buys 2 more cans of tennis balls. Each can has 3 tennis balls. How many tennis balls does he have now? This is sort of a trivial question for humans. If I were to ask someone, their sort of chain of thought in their head would be something like the following. Roger started with 5 balls, 2 cans of 3 balls each is 6 balls. 5 plus 6 is 11. Okay, so the final answer is 11. And now, so the next question is, how do we get the language model to produce this chain of thought that humans would have and to solve the problem? So you can see on the left, in standard prompting without chain of thought, you come in with you have these XY exemplars, so the question and then the answer, and then you come in with the inference question. In this case, the cafeteria has 23 apples. If they used 20 to make lunch and bought 6 more, how many apples do they have? And the model unfortunately gets it wrong. So the method that we propose to sort of enable language models to generate this chain of thought is super simple. All you do is you add chain of thought into the exemplars in the prompts. And then the model learns to output a chain of thought before giving the final answer. Here in this example, the model is given the same question about how many apples are in the cafeteria, and then it generates its own chain of thought to solve the question, and then it gives the final answer. And the way that we write the exemplars in the prompt is that we just manually write them based on how humans might loosely reason about it, and then we include them as part of the prompt. So let me just do a quick demo. I think it's always cool to sort of see how you could play with this yourself. Am I showing? Let me know if I'm not showing the GPT-3 API. So, okay. Here, let me try to make it bigger. Great. So here's the GPT-3 API. I think just yesterday, I saw somewhere that you could sign up for this and no approval is needed, so you could start using this immediately. And there's free credits, I believe, up to a certain limit when you first begin. So the point is, I think it would be pretty easy for you to just try this yourself at the OpenAI playground. So this is GPT-3, this is the TextDaVinci 001 version, and we're giving it a prompt. Basically, we want to solve the question about apples in the cafeteria, and then this is sort of the standard way of doing it. So you give the question, answer, question, answer, question, answer, and then question, and the model has to give the answer to the question. So here the model gets it wrong, and what chain of thought proposes is just super simple. So you take the same exact prompt, except you add in chains of thought for each exemplar. So here's a chain of thought. Here's a second chain of thought. And then here's the third chain of thought. And now when you ask the model the question, I hope that's right. Yeah, so okay, yeah, so that's right. So the model says the cafeteria had 23 apples. Originally, they used 20 to make lunch, so they had 23 minus 2 equals 3. They bought 6 more apples, so they have 3 plus 6 equals 9. The answer is 9. I'll show another quick example. So let's find this one here. So here's a really easy task again. So basically you take the last letters of the words in a name and concatenate them.
Roger
So
has a
here
question.
You want to take
Oh,
L
okay, hang
and
on.
S.
Go for it.
One question I had as I was watching that is that the examples of how to kind of prompt for a chain of thought seem to be somewhat related to the prompt that they were testing on. And I'm just wondering how generalized this chain of thought prompting can be. I don't know if anybody's heard of any other type or tried it.
I haven't heard of it before this. Anybody else?
Yeah,
'Cause
meaning
it
if you
seems-
go from a set of exemplar that are addition, subtraction, and then you have a multiplication one where you bought 3 of 6, would it be able to do the same thing?
Or even a chemistry one that happens to be, same type of thing. Think it through. Don't just jump straight to the answer. Okay, I just wanted to raise the comment. I did notice there's also some papers in this area, if this is an area that we're interested in as well, where people are trying to prompt it to break bigger problems into smaller chunks, and then, prompting for each of the solutions to each of the chunks one at a time.
Yeah, that's a good reference, Roger. I think generally what we've seen is that if you ask it to make smaller steps, because it's just a language model and it's not a logical model, that it seems to do better, So like whatever, like tell me how to, fill in the blank, make a peanut butter and jelly sandwich or whatever, right? But if you say, tell me step by step how to make a peanut butter and jelly sandwich, that prompt generally works better, for example.
Right. Okay.
Do you think
Thank you.
Do you think it's because it gives it I don't know what the right way to phrase this, but a longer tail of, smaller steps rather than trying to make the big leap? If that makes sense.
Yeah, so
I think it
the
does.
model's autoregressive, and it uses everything it said as context for everything it's going to say next, right?
Makes sense.
So, I mean, like we're joking in the chat about show your work, but like, yeah, if you tell the model, like first try to do 23 minus 20, and then do your answer plus 6, it's going to be more successful than if you just say do 20 minus 3 plus 6 in one fell swoop. Even if you I think even if you just explicitly forget about the word problem, just said like, what is this plus that minus this plus that, it might get it wrong. But if you do it just 2 at a time, it will get it right.
But is it
I mean,
because
I think the question is, why is it able to do the math? Is that the question at all?
why isn't it able to do the math in Ted's more complex example? But if you break it down into step 1, step 2, step 3,
If I could take a slightly different angle on that, Ted, maybe it's that when you look at kind of the training data that were used here to train a language model, the number of examples that are something around 3 take away 2, 3 minus 2, 3, then do 2, thinking about it from kind of a transformer and that action being somewhere in the middle of those 2 words, the likelihood of that, there being a bias within the model to knowing that the actual math answer is 1 is going to be a lot higher in a language model that's not designed to do math or designed to do chemistry, or designed to decompose words, then the likelihood that you have a 4-step process that has 1,000 examples from your relatively unbiased data set as an input.
Yeah, I'd like to add this. It's an autoregressive model. All it does is emits the next word and the next word and the next. So when you break a math problem into sentences, it's very much like we do it with very small children. You make it a narrative. Language models are good at narrative, and I don't think it's solving the math problem. It's just coming out with the narrative whose pattern you have just trained it on.
Exactly.
Yes, I agree.
Exactly. Yep.
Yeah. That's some good conversation, guys. That
Yep.
makes
And then
perfect
briefly, I
sense.
just want to reiterate, I think this is the comment I made last week. If I said to you, okay, add these 12 2-digit numbers, and if you get it right, I'll give you $1 million, but you can't use any paper or anything like that, right?
Mhm.
You would still virtually use paper. You would add the first 2 numbers in your head, you do whatever. Then you might say, for $1 million, I'm going to repeat it. I'm going to add them in the reverse order. I'm going to whatever. I'm going to check my right. And until you're absolutely sure you've got the right answer. And then you're going to say, the answer is 345. Give me my money, right? But an autoregressive model has no option to use any short-term memory, any scratch paper, anything. The only thing it has is the words on its left that Asif, sorry if I'm pronouncing your name wrong, said. It's autoregressive. So in order to have scratch paper, it has to actually say aloud all of its intermediate thinking.
So does that imply, Asif, that the exemplars need to be similar to the prompt question then?
I would say so. So one counterexample you can try is deliberately give a word reasoning that is incoherent, and give a few such exemplars, and then see how the chain of thought continues there. Because it's not thinking. We have to remember
That's a good
that
suggestion.
humans do not think. Yeah, it's just following patterns of word generation.
Mhm.
I'll say, I think if you show your work for an addition problem and then you give it a multiplication problem, I think it'll still be helpful, but not if you give it,
I think this is going to be really good for couples counseling, right? Because if you take, when couples are fighting and the logic that they use and just how completely fucking ridiculous it is, and then you can use the ChatGPT as the counselor, and if the counselor comes back with garbage, that's your fault, right? And it's just it's an objective measure of what kind of garbage you're spitting out in your relationship. I think it's perfect.
That's a very good example of training it with incoherent things and then expecting good results.
That's exactly right. That's exactly. I think it'll be.
Yeah, but
my relationship will be fine, but you guys, I'd be loath to try it on your guys.
Would it does it bill you $200 an hour for that session? All right.
I mean, that's the business model. That's what I'm saying,
Not
man.
yet.
This isn't an actual counselor. It's just a service that you
Yes.
pay to be objective between you and your wife or you and your husband. You both type your shit in, and it gives you both bullshit scores, and then it's the objective person that allows one of you guys to be right, which is what's really important in relationships, is who's right and who's wrong.
Yeah,
as I keep telling my wife.
This reminds me of, do you guys remember Eliza back in the day? Really early thing. And when it couldn't figure out what you were asking, it would say, "Tell me more."
Yeah, exactly. All
and
the
you
time.
do it. Yeah, and it would do it enough. And finally, it had this very narrow knowledge base. You'd get something that, oh, well, now that you did that, the answer is 7 or something. Some magic. Anyway,
Jerry, are you referring to the one built into Emacs? Conversation.
Yeah, I don't know if it was in Emacs or not. I saw it as something, and I'm dating myself now, back in my early computer science days in the 90s. So
it was an expert. It was the peak of expert systems, if I remember correctly.
Right. It was going to be the next best thing, and it was going to take all our jobs, just like ChatGPT. But
I've spent countless nights having philosophical conversation with Emacs.
All right, before we go too far down this alley, does anybody have an objection if I restart the video or move it on? No? Okay, I'm gonna hit the play button.
I think Sally's
Great
wife has
company.
an objection, but we can go on anyway.
Or should we ask ChatGPT?
I'm hitting the play button, guys.
Yeah,
I'm not going to get Dave into trouble.
And here we want Elon Musk, but unfortunately it gives sort of SK. And then when we do chain of thought, all we do is we add in this sort of intermediate step that shows the model how to do the problem. And then the model can correctly generate NK.
You know, that I think matches what Asif said, right? It's just like you have to kind of hold its hand a little bit and then it kind of goes, oh, I can do that again. Anyway.
Okay, so back to the slides. Great. Before I move on to the empirical result, are there any questions on what the sort of method I'm proposing is? Okay, cool.
Maybe Jason, I'll use this time to ask a question.
Yeah.
Maybe you're gonna talk about this later, but I'm personally curious about to what extent the model would be sensitive to the articulation of the chains of thought that you had before the final answer.
Yeah, that's a good question. Let me come back to it. I might forget at the end, but if I forget, please remind me again. I think I could show some results, and the results might help contextualize my answer to that question. Okay, great. So I'll start with the empirical result on grades. This data set called GSMAK from OpenAI. It's basically a data set of grade school level math word problems. So they're anywhere from like 2 to 7 steps, and we would all be able to solve them pretty easily. And again, we have a plot where model scale is on the x-axis and solve rate is on the y-axis. And then we have the blue dot for standard prompting and the pink star for chain of thought prompting. So for standard prompting, you can see, okay, increasing model scale sort of increases the performance a little bit, but it's not like a huge increase. And then on the other hand, for chain of thought prompting, the pink star, there's upward scaling curve where scaling up the model leads to substantially better performance, in this case, like around 15%. And when you use better data and scale even further with the Palm model, we get something that was a bit unexpected, which is that by scaling to 500 billion parameters, we actually beat both fine-tuned GPT-3, 175 billion, and the fine-tuned SOTA at the time by a pretty decent margin. And just for context, around 60 is the average performance of like 9 to 12-year-olds on the data set. In retrospect, data set was funny because like when we had the original paper, we only had lambda, and we were trying to argue that this was like a positive result of 15%, and then once Palm came out, that result was like a pretty low result. Anyways, I think the plot is quite important because it sort of underscores how scaling is crucial to the success of chain of thought. Here results on another task. So this is the task we just saw where you concatenate the last letters in someone's name. And again, we have model scale on the x-axis and solve rate on the y-axis. And so here in domain means that the few shot exemplars have chains of thought of 2 word names, and then the model has to do 2 word names. And the model gets like basically 100% when you scale to 500 billion. And I think the cool thing is that even when you test on 3 or 4 letters, which is out of domain, so few shot exemplars only have 2 word names, and then at inference time you have 4 word names. excuse me. Chain of thought still has a decent solve rate for these sort of out of domain examples, even though only 2 word names were shown in the prompt. And you can also notice that the performance is basically 0 when you don't use chain of thought for this particular task. And we had sort of over 10 tasks in the chain of thought paper, but I'll highlight one last one here, which is that chain of thought can sort of be used for any task. So, any task in principle has some reason or explanation, even though it can be a very simple one. This last task is sort of this task that requires like world knowledge and common sense reasoning called strategy QA. And here's 2 examples of real model outputs. So on the left, the model compares the sizes of a basketball and a sandcat's ear, and on the right, it makes this connection between oysters and guitars. And again, this leads to a strong result that beats prior fine-tuned soda using Palm, though there's still a gap to human-level performance. Great. Let me try to address your question, Daniel. So the question is like, how robust is the model to different types of, like different people writing different shades of thought? I think the answer is really task dependent. So there may be some tasks where someone could write a chain of thought that is like really suitable for like stuff like steps that the model knows how to do, whereas other people might not be able to write such a chain of thought. So for example, when we were doing the original chain of thought paper, we had like this task that was about flipping like reversing a list of 5 items. And like me and my manager had tried like, getting like writing prompts for this to work for like, I don't know, like a week or so. And I happened to tell like, even though we couldn't get it to work for whatever reason on Lambda. And I happened to like tell the person next to me and he was like, what, there's no way. And then in like 30 minutes, he like came up with like some prompt that was able to solve like reversing a list of 5 items in like 30 minutes or something. So I think for some tasks, there's sort of some magic in like what goes into the exemplars. But for a lot of tasks, you could sort of write any chain of thought and it would be pretty similar to what someone else would, the performance of what someone else would write. So for this, strategy QA example, and let's see, for like these math word problem examples, we found that the performance was like relatively robust to the chain of thought exemplars that people would write. Is that helpful?
Yes. Maybe if I may follow up on that.
Yep.
When you were referring to coming up with a prompt, I think you mentioned that there was some difficulty coming up with a prompt for, I think, strategy QA task. Were you referring to coming up with the exemplars or the chain of thoughts for each exemplar?
Oh, yeah. So the strategy QA one, we didn't have any trouble. We sort of just had one go at it. I didn't really do any optimization because we just took examples from the training set, and then I wrote like the prompts. Or I wrote the chain of thought annotations for the prompts. It was the reversing a list of like five items. We had the exemplars, it's easy, we can just generate them, but it was the chain of thought that sort of made a big difference in whether the model could do it or not.
Can you pause on that real quick?
And then
So this reminds me a lot, Jerry, you mentioned expert systems models and early language models, which were, token and class based. And if I remember right, like there were frame-based models and token and class and expert systems, and there was a huge debate. We talked about it in this meetup a long time ago. What's the guy's name from MIT who used to just argue so incredibly strongly that the concept of restricted domain in language is like such a fundamental no-no. What's like a no, is it Noam Chomsky? Is that who I'm thinking of? He was like super religious about that.
Noam Chomsky is from MIT. I don't know if he made that argument though.
And what I love about this though, and it's just I'm asking myself as I'm listening to this, are we essentially accomplishing the same thing at a runtime, which is very, very different than being in the model, by the way, right? Like using the exemplar to do that, and how fundamentally different that is to be, you know, kind of expressing scope and expressing expected structure of your answer at runtime. Just how really interesting and powerful that is in contrast with the way that we were looking at this 25 years ago, you know, again, expert systems being really, really far at the front, where it really was like expect sentence in this modality, and then you had synonyms that you could substitute. And as long as you asked the question with those synonyms, it would kind of figure it out. But that was it. But that seemed at the time, you know, like life-changing. This, because it's at runtime, just feels so incredibly powerful.
Dave, if I may rephrase so I understood it. See, Chomsky, if I remember, his thing was that of a universal language, that underlying all languages is a universal structure. So to the extent that there's a universal structure and all languages will share it, the way we reason, I believe his concept was, we are conditioned to reason in a particular way by the structure of our brain. And in some sense, the output of our brains is what these machines are learning from. So they're learning to reason along those same structures. Is that how you're connecting the dots?
Yeah, and that a lot of language models that Noam Chomsky did not, he spent a lot of time talking about what he didn't like.
Yeah.
That what he didn't like was when people made these like artificial constraints on the input side, because he felt like there was to your point, kind of an underlying structure that would be discovered that would be discovered instead of trying to artificially force the model into some direction. And so this, although it's not directly related to anything that Chomsky did, almost kind of justifies his or agrees with his underlying assumptions.
Yeah, I believe so too. That's quite an observation, actually.
So sorry, I just didn't as I'm listening to this, that just keeps going through my head. And I forget the guy he used to fight with across the hall, but that battle is very much in my mind. He used to post stuff on the other guy's door. Like, it was truly a battle.
It would have been great if they would have had the internet and forums to sit there and fire flames across the campus or whatever,
and webcams on each of their doors. But he would literally like walk over to the other guy's door and staple something.
Actually, considering that Chomsky did so much work on the structure, on the linguistic structures and so forth, he must be having a lot of thoughts on these language models. Has anyone dug into or interviewed him on what he thinks?
He's pretty old now.
He is, but he's very active.
Is he? Okay. No, I've not heard anything from him.
He's super opinionated, so the fact that we don't have it is kind of surprising.
Yeah, it may say something about his ability in this area. I'm going to move us along, okay? Okay. If I can get my mouse over to the screen.
Is it so? In that, I guess, is it fair to infer from what you're saying that to make chain of thought work, it's probably the trickiest part is not finding the exemplars, but rather finding appropriate chain of thought phrasings to make it work?
Yeah, so again, I should say it depends on the task. So for the math word problems task, this like models basically can't solve like a multi-step math word problem without chain of thought, or it's very challenging for them to do it. So even if you write like really low quality chain of thought, it's still going to be better than the baseline of not using chain of thought. On the other hand, like for a task like sentiment analysis, the task is sort of so easy and the baseline is already really high that even if, like with good chain of thought exemplars, you might get worse performance. So it really depends on the task, like how well a chain of thought improves the performance.
Thank you.
Great question. Cool. So yeah, let me just summarize some of the benefits of chain of thought. So first, producing a chain of thought in principle allows models to decompose multi-step problems into intermediate steps, which means that for problems that require more reasoning steps, the model can allocate additional computation. Second, a generated chain of thought is sort of this window into like what the model is trying to do. And it suggests how the model might arrive at a particular answer and provides opportunities to debug where the reasoning path went wrong. Third, chain of thought prompting can be used for a range of tasks, such as math word problems, symbolic manipulation, common sense reasoning. And it's applicable, at least in principle, to any task that humans can solve using language. And then finally, chain of thought reasoning can be readily elicited in sufficiently large off-the-shelf language models simply by including chain of thought sequences into the exemplars of few-shot prompting. And I think this prompting point is maybe the most important answer to the why now question. So just to be clear, the idea of producing intermediate steps has been thoroughly explored in prior work via fine-tuning. Here, there are some examples. But the setup is kind of non-ideal because you need this large data set for fine-tuning that includes intermediate step annotations. And then after you fine-tune the model, it might only work for one task. With prompting, all you have to do is write a few annotations, and then a single large model still maintains its generality across a range of tasks. And finally, here's this hand-wavy figure for a chain of thought that I made to try to capture the essence of the paper. So on the y-axis, there's some spectrum of NLP tasks that we care about. It's pretty arbitrary, I guess. And then on the x-axis, we have increasing model scale. And the blue shaded part represents tasks that language models can do with standard prompting. And you can see, as you increase the scale of the language model, the number of doable tasks increases. And then the pink shaded part represents the tasks that chain of thought models can do either with standard prompting or chain of thought prompting. And the goal now is to say that this includes like, math word problems, symbolic reasoning, and challenging common sense reasoning tasks. And so the point is chain of thought prompting unlocks another set of tasks that language models can do. And it sort of happens at around the 100 billion parameter model scale. Great, so I'll pause here for a second if there are any questions. Otherwise, I could move on to a couple extensions.
Yeah, so I encourage everyone, if you have questions for Jason, please voice it now. We are super lucky to have him here, so let's use this opportunity.
I have a question.
Yeah.
So there was a paper that we discussed in class before where they were talking about
I don't know if you meant to pause on purpose, Jerry, but I'll take the opening because I was thinking about making a comment. So he had said that like
the correctness of the prompt in improving the accuracy of the model. So it was found that even if you randomly assign a few prompts that you give the model, it will improve the performance compared to like a zero-shot case. But in this case, is the correctness of chain of thought important? Like, did you do any study of that?
Yeah, that's a great question. I couldn't hear Clay, but this is this is Sewon Min's paper, right?
That's right.
Okay. Yeah, so that's a really interesting paper. Basically, if I understand correctly, like the paper showed that if you replace the labels with like random labels, it's like almost as good as like having real labels, right? I think you might see a similar thing in chain of thought prompting, but again, it sort of will depend on the task. So let me try to give an example. So we did an experiment where like for math problems, we just like swapped the numbers randomly. So the chain of thought was still correct, but like the numbers were all wrong. And that only hurt performance by a little bit. So in that sense, it's consistent with the findings of that paper. I think for other problems, you can't mess up the chain of thought completely because I think the model is like making more use of the intermediates. Like the intermediate steps is sort of more degrees of specification than the original few shot prompt, right? So for example, I think, for this one here, I don't know what would happen if you change like N and K to other things, but I would guess that might hurt performance. Like if you said like the last letter of Elon is E and the last letter of Musk is N.
Yeah. So I just tried the same example and it does correctly. Like I changed N to P and K to Q and it still showed NK.
Oh, okay, great. So if it's robust, that's great. I can't think of an example now, but I reckon like maybe surface level changes don't hurt performance, but if you were to change the structure of the chain of thought, it might hurt performance. I'm just guessing.
So like raises another question that what is the meaning of emergence then the emergent property? What is emergent? Is it really
Hey, Jerry, can you pause,
understanding from
please?
the prompt or like the chain of thought, or is it just using?
So one thing I wanted to add is now that we've seen widespread use of ChatGPT, which is still ultimately right a decoder only autoregressive model, we've just seen many more experiments than PhDs and professors can do. So at the extremes, and I'm sorry, there's a lot of gray area in between, but at the extremes, if you do something like math problems where you switch around the numbers, or you say 2 + 3 = 6 in your exemplar, then it's probably not really going to hurt very much. But if you word for word, token for token, include things in your prompt, it is definitely, we've seen these models copy things, and they have to because if you say, I'm telling you a story about someone named Ernie Brown and blah, 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 it needs to copy Ernie Brown in its response. So there's a certain amount of copying that's like absolutely required. So in your prompt, if you say 2 + 3 = 6 and you give it a new word problem and you say 3 bananas and 2 pears, how many fruit, it might say 6 because it's literally seen those exact words. But if you just give it some other random addition problem, I think that's the pattern that we've seen with generalization. I don't know if everybody was familiar, but I thought I would just comment on that.
One quick question,
yeah, that's a great
Ted.
question.
I'm sorry. You said copying. What do you mean by copying? What kind of behavior you referring to? Means temporary storage of memory somewhere, or you're referring back to the model? What do you
say attention? Yeah.
Attention.
Yeah,
Okay.
yeah. So if you look at the transformer circuits work that's being done at Anthropic, are you familiar with that?
A little bit.
Yeah, I can try and find a link, but I don't do a good job like talking and doing Google searches at the same time. But basically, what they've shown is that literally one of the behaviors they see when they analyze, and they're doing smaller, like one layer instead of 6, 12, 24 layer transformers, right? Mm-hmm. One of the behaviors that they see is this literal copying. So you can have a token that's at position 2 in your prefix of 25 words, and then you ask it to continue the string, and you'll see, like the example they did is that some excerpt from Harry Potter, for example, okay?
Mhm.
And when the transformer sees the word Harry, it actually attends to, like, oh, there was a Harry in my substring on my left, my you know, I don't know whether you use the word prompt or prefix or what at this point, but there's a Harry in my prefix. And so the first behavior that's learned super early is it just knows that, oh, there's a Harry. But the interesting behavior that they've learned is once you get a slightly more trained, more complex transformer, now whatever word appeared immediately after Harry in the prefix suddenly has a huge probability of appearing next in your output. And so it's very much saying, I see the word Harry, I'm going to follow it with Potter. There's like a super high probability it's going to follow it with Potter because it is literally copying the token that came after Harry in my prefix.
Got it. Basically, all the attention in the prefix means whatever it is trying to predict what next is coming, everything on based on the prefix, which is AKA kind of temporal knowledge, or the set of words to come up with a meaningful outcome of what next that could be. So that's what, if I'm alluding into copying, means. Okay.
Yeah, but the crazy thing is, right, like you can have a lot of things in the prefix. You could say Harry went to the store, Harry this, Harry that, Harry that, Harry Potter, Harry this, Harry that, Harry Potter. And, the transformer has to have enough language knowledge to know when am I going to actually just use Potter and when am I going to like put a verb there next and when am I, you know what I mean?
I see.
What's kind of amazing is these large models make those decisions. They're not so rigidly, stupidly always just copying the word after. If it were that, you would just have a bigram model, basically.
Mm-hmm.
I would resonate with that, actually. Increasingly, it seems that they seem to be beginning to grasp at the linguistic structures in languages.
Yeah, it's cool. So, we don't have to write some context-free grammar. It's figuring enough of that out, and then you layer on these other kinds of behaviors.
Right. One thought that occurred to me, and I don't know if you would agree. See, if you look at the classical transformer architecture, to the extent that you pay attention to certain things, and then in an autoregressive model, you emit the next thing, that attention begins to look very, very close to transient memory or transactional memory of a human thinking, right? And you're utilizing all that is sitting in the transient or the transactional memory to generate the next thing. Just a thought that you're taking that and imposing the learned structure of how to use that memory to produce your next sentence. Now, from what I remember, the understanding in neuroscience today is that our thoughts are a response to memory. There has to be enough memory for you to have a coherent thinking process, and you begin to see some resonance between the two.
Yeah, that's a cool train of thought. I don't know if I can add to it. What I will say briefly is that, hey, RNNs, LSTMs, they have a transient memory. Transformers are clearly doing something more complex with their ability to look back than that. There's something that has them be more successful. I don't know if we really know what it is. I mean, it's clear they have a more explicit ability to go back to previous tokens, whereas with LSTM, right, it's just over time, it's just passing this one thing, and it's, so is it just that it has a more clear, direct random access, or is it that fundamentally you can do patterns with attention, like things like copying and things like, whatever. One of the other things I thought was really cool in that transformer circuits work, and I'm sure they've extended it, they keep, writing new stuff, but they saw particular transformer subcircuits that would zero out portions of, because remember, transformers, I feel like this gets under talked about, and the Anthropic people help me, it's a ResNet. Okay. So you're only adding onto this data bus, as it were. And so one of the things they explicitly saw, it's multi-headed and everything, but there were places where the head would say, oh, take that token that's at my current spot, multiply it by -1, and then stick it onto the ResNet, which basically means it's zeroing out this register so that the next attention can put what it wants into that register. I thought that was like really cool behavior.
That's interesting. Actually, I don't know. Now that you mention it, it reminds me of an interesting, the bottleneck principle that for computers to learn. There was this paper, 2018, 2019, that there's a bottleneck thing happening for these machines to learn. They have to come up with a very compressed or bottleneck representation. And this seems to be like, I believe the professor, he was from Israel, and what he was saying is that to learn, you must forget. And what you are saying, multiplying by -1, seems to resonate with that paper, that transformer is trying to forget what is inessential so that it can now focus on what is essential.
Yeah. Jayanth has his hand raised, so I don't want to like keep going too far, but like,
Yeah, thank you.
I can't remember which paper, but there definitely was a paper where they said either data size or model size early on, you just see data memorization, right? And then you should see something sort of like pattern memorization, and then eventually it goes to generalization. So at some point it has to forget the data memorization. At some point it has to forget the pattern memorization and go to the actual generalization. But in this case, I don't know, because that would just be sort of like the weight updates, forgetting earlier things it was doing or whatever. But in this case, it is literally saying, I have limited bandwidth on my data bus. I'm going to clear this portion out so that the next layer of transformer can write what it wants in there.
All right. Interesting.
Yeah. Wow. Thank you.
So Janet, did you want to have a comment?
Yeah, so I have a question. I'm trying to understand the AR autoregressive model better, right? So I think one of the people that asked a question in the video gave a wrong letter as the last letter, right? Was that the example? Does anybody remember?
Yeah, they said instead of the last letter of Elon is N, they purposefully gave the wrong letter.
P or something, right? Yeah.
And then they asked it to do they asked it to then do it for a new name.
Right.
But they said it still got it right.
Right.
Because it showed the pattern of decision making, even though its actual letter was wrong.
Yeah. So a couple of things. So suppose instead of saying last letter, if you say first letter or third letter or something like that, and in the prompt, but ask for the last letter in your question, would it do okay? That's one question. Another.
I think we don't know for sure, but generally what he said is any kind of prompting beats no prompting.
Right, that's true.
And then prompting that matches the pattern, like, oh, it's addition of two numbers or whatever, is going to do, slightly better. But that forcing it to take smaller steps seems to be helpful regardless.
Yeah.
And that it's robust to whether you would have this set of steps and I would have a different set of steps, that like different users that did prompting, it seemed to be relatively robust to who was writing what kind of prompts.
Yeah.
Jane, to your question, I would bet that the answer is yes. It would give the right answer, even though you were telling it the middle letters.
And what in the AR model helps it to do that?
See, last word is something that it has learned. It's very common in human vocabulary. So all it is learning is the reasoning part, like, if the middle letter of the first sentence is this and the middle letter of the second word is this, then what is the last, what is the concatenation of the last ones? Well, it has figured out the concept of concatenation and it knows what the last letters are. So putting the 2 and 2 together after that is not even reasoning. It's just like, one would imagine it should be able to do that.
Okay, yeah. And the other question is, if there's some confusion, because here the letters are all unique, right? Is there, or is it just that the fact that it's the last letter helps it, because the wrong letter example may be the answer here. So because if you have, I can't think of a word, session, if you say the first letter of session is S, there are 3 S's in session, would that trip up the model?
So Jayantha, I'm going to answer your question slightly differently, okay? Because I don't think in the prompt, I don't think it's paying that close attention to whatever the heck you're doing in your example and the letter S and whatnot. I think for me, what this chain of prompting paper is pointing to is that it's trained on all this language, and even, excuse me, even non-mathematical language, just people writing essays about Shakespeare. There are a lot of paragraphs that have the form, like if P then Q, if Q then R, therefore, because of P, R. You know what I'm saying? Mm-hmm. So there's just a lot of sentences that are the form of, this means that this person is a bad person, character A did this, therefore character A is a bad person. You know what I mean? There's just a lot of language that's structured like that. So anytime you can get the autoregressive model to talk in baby steps, it knows how to emit those kinds of logical sentences that say if P then Q, if Q then R, then R, right? And so that's why I think it does well, even though it may not have that many like word math problems in its thing. It knows how to say, like, let me just take the 23 apples and subtract 20. I know how to do that. It knows how to do that as a separate thing. But if it knows how to do that and it knows how to add 3 and 6 apples, then it knows how to say the answer is 9 apples. But if it doesn't do the intermediate step, again, because it has no working memory, it might just try to leap, and it's going to leap to a credible sentence, right? The credible sentence is the answer is a number, apples. Mm-hmm. So the structure of that sentence and it's, it's not going to say something completely garbage like my car is blue, or, the answer is, bananas, apples, right? It's going to have that right structure, but to get the number right, that's like a slightly different phenomenon. Anyway, that's sort of my take on why having it speak out in baby steps helps it, because it has a lot of training on sort of that logical argument stuff, even if it's not all mathy.
So is it that I'm just trying to see what's, kind of trying to look under the hood. Does it help it in the sense that at t minus 20, it figures out the answer to the first sentence, at t minus 12, it figures out the answer to the second, and so on, and somehow puts it together? Or what is happening underneath that is helping the model? Does that question?
Why don't we watch a little bit more and see if they come to that? I sort of remember that.
You do? Okay. Okay. Yeah, sounds good.
Okay.
And I guess when I say emergent, I try to use the least controversial definition, which is like emergent performance, which doesn't make claims about whether the model is like truly understanding the task or how it's using the chain of thought. All we're saying is the performance happens to increase at a certain model scale. I think the question of whether the model is understanding exactly like a way that a human does is pretty complicated. I don't want to make such claims at the moment because of things like this, where like you can just, I guess you could like ask a human to like complete the next word, and if you shuffled it, maybe they would still get it correct. I don't know, like it's a very complicated question that I don't have a great answer to. Great. I'll move on if there are no other questions.
I have a question.
Oh, yeah, please.
When doing error analysis, do you find that the model, when it makes errors, is it self-consistent, or do you find that individual steps are okay and then the final answer answer is what's wrong?
Yeah, that's a good question. Let me see if I can find, I think I had a slide somewhere about this. So the general answer is, I don't think there were very many instances where like all the reasoning was correct and then the final answer was wrong. Just because like if it was easy to, if the model was good enough to get all the reasoning correct, it was probably good enough to like make that final step. Basically, there's no like good categorization of errors. There are some, we try to do some categorization. So like, you know, semantic understanding, which means like it didn't really understand the problem correct, like fully, or try to use the right solution. There are some errors where like one step was missing, where like if I could go in and modify one particular sentence in the chain of thought, then it would be the correct answer. And there are some other types of errors like hallucinations or repetitive outputs. But yeah, generally there's like a range of different types of errors, and it would probably also depend on like what the task is. Cool. I'll talk just briefly about a couple of follow-up papers that have come up. So yeah, first I'll talk about a work called self-consistency. And this is, at least to me, it was quite surprising because it's like such a simple idea, but the performance improvements are pretty strong. So the idea of self-consistency is like there's a lot of different ways of like solving a multi-step problem. And there's this quote, all roads lead to Rome. And so here are some of the key ideas. So first, you know, the generated chain of thought is usually not scored. So like you didn't have to generate it. We like the evaluation metric only cares about the final answer for most of these NLP tasks. So we could just ask the language model to like generate a diverse set of possible solutions. So not just one, but you know, up to 50 or 100. And if you know a majority of them lead to the same answer, then it's more likely that that's the correct answer. And so here's sort of a motivating example. So you know, again, we prompt the language model in a few shot setting about a math question. And then we can do like, you know, greedy decoding as we did in the chain of thought paper. And here the model happens to get it wrong. So instead, what we could do is this. So given the same input, you can generate like a lot of different reasoning paths. So only 3 are shown here, but you could do up to 50 or more. Just by doing temperature sampling or your favorite, you know, random sampling strategy. And here it turns out that some of the answers are correct, the ones shown in green, and some of the answers are wrong. And note that like we don't really care about the reasoning path in this case. We can just look at the final answer. And then once you have the final list, the final answers, you can just use a simple heuristic of taking the majority vote. And then you can just pick whatever the majority vote is. Let me just try to show this real quick. Because this is random, I'm not sure that'll work, but let's see if it works. So, okay, again, here's the chain of thought prompt. And then I just asked like a question. So Tracy used a piece of wire 4 feet long to support tomato plants. The wire is cut into pieces 6 inches long. How many pieces did she obtain? So the answer is 8 because you know it's like 48 feet or 48 inches, and then you divide by 6. And notice here we're doing temperature sampling. So we set a temperature, and then we can ask the model to decode, and every time we ask the model to decode, it'll give something different. So let's try here. So this time I decoded something and that's wrong. Try again. Great, that time it's right. And then if it's right again, then I can stop the demo. Great, so basically we generated 3 random samples. 2 were correct, 1 was wrong. And then we could just take the majority vote of the 3, which was 8, and then in principle, not in principle, but empirically, this gives better performance. Okay. Is that clear? I'll present a result soon, but if there are any questions, feel free to raise your hand. Okay, so here are some of the results on the typical reasoning data sets that we evaluate.
This sounds a lot like just with random dropout. So when you have a neural network, we use random dropout to during the training process to help the neural network not overfit to something, but then turn it off during the inference phase. If you leave the random dropout on during the inference phase and ask the neural network to make the same inference again and again, because of the random dropout, it's like a slightly different model that's making every prediction. And if each of the slightly different models are making the same prediction, then that's a sign of like the model is really sure about what the actual prediction is. But if each of the slightly different models have different answers, then that's a sign that the model is guessing at this point. And this feels a lot like that.
Yeah, I think in this case, it's just not quite as destructive as dropout. But basically, like, you change the temperature and you randomly sample. So
do we know what temperature really refers to?
Thank you for asking that.
Yeah, that is kind of a question, I guess, right? Yeah. It's something to put down on my list of things we should.
yeah, I don't know if they just default to regular softmax temperature. What is that, 1 or whatever? I don't know.
I don't, it's temperature. Who know, that's a good guess, but what's the right guess? I guess I don't want to, let's leave that for another day, but I jotted myself a note to find out what that was and sometime be able to come back.
The other thing is just, some of these models, they do like beam search or whatever. So they're not actually emitting each token one at a time. They're storing up a few tokens to see if the second and the third tokens will have logical high probability completions. And if somehow choosing this word paints you in a corner, then a different word might actually have a higher total beam value, even though it had a lower first word value.
Right. Yeah, as it just goes down the chain of reasoning or whatever that it's using. Yeah.
Gary, in the GPT playground, that you can adjust the temperature setting, and if I recall, the description of that was basically how tightly it conforms with the prompt. So I think it's kind of, do you select, the maximum probability, or do you spread it out a bit?
Okay. Thanks. Right. I'm going to move us along so we can finish this up here. We just have a few minutes left.
And here's the GSM 8K dataset from before, shown in the purple box. And you can see, okay, with greedy decode, it's like 56.5. But if you use self-consistency, the number goes all the way up to 74.4. So this is a pretty big margin just for like a simple trick of, sampling multiple times and taking the majority vote. And then using the PaLM model from Google, it beats state-of-the-art on 8 of 10 reasoning tasks that we evaluated. And I'll show one more interesting result about self-consistency. So an important part of large language models is that we want them to be well calibrated, which means that they ought to be able to give a confidence about a prediction and have it be relatively close to like how often it's actually correct. So in this figure, we show that the consistency of the decodes, which is like the percent of decodes agreeing with the majority vote, is nicely correlated with the accuracy. Okay, so this is another paper called Least to Most Prompting. And least to most prompting is basically a hierarchical prompting method that gives you even more degrees of freedom for prompt engineering. So here sort of there's like a math question on the right about how long does it take to how many times can Amy slide down the slide. And in the first stage, we decompose the problem into like 2 subproblems. So one is highlighted in orange, how many times can she slide before it closes? And the second is highlighted in green, how long does each trip take? And then we take those sub-questions and we refeed them back into the model in a second stage. So in the second stage, first we solve the first sub-question, how long does each trip take? Language model says each trip takes 5 minutes. We take that answer, we feed it back in, and we append it to the answer to sub-question 1. And then we ask the second sub-question, how many times can she slide before it closes? And then it gives the final answer. So basically, we're decomposing the prompt, and then we're solving the problem in like this hierarchical process. And it turns out that least to most prompting works really well on compositionality data sets. So here is an example of a data set called scan. Basically in scan, a model has to translate a command, like look thrice after jump, into different action sequences. And here's sort of an example of least to most prompting where the model solves the problem jump right twice after walk. So you can see first it solves jump right. It uses that output to solve jump right twice, and then uses that output to solve jump right twice after walk. So here are some empirical results. You can see in the highlighted box there that the accuracy is really strong on the scan data set. So even when basic standard prompting and chain of thought are really low, least to most solve this with 99.7% accuracy. Okay, I'll briefly go over 2 more papers. The first is multilingual chain of thought prompting. So we basically took the GSM-8K data set of math word problems, and we asked human translators to manually translate them into 10 different languages. And here's an example of one of the questions in Bengali with the few-shot prompt. And for those who don't know, Bengali, I think, is the 7th most spoken language in the world, but in NLP standards, it's an underrepresented language. And here you can see the model can actually correctly do the chain of thought reasoning in Bengali, which is a nice demonstration of compositionality because the model was not specifically trained to do Bengali or to do reasoning, and it learns to sort of combine those 2 skills. Here are some quantitative benchmarks on the math word problem benchmark. So the x-axis is the frequency of each language in the pre-trained data set by token percentage. So you can see English is like 80, and then we have some what we call high resource languages like Japanese, Chinese, Russian, Spanish, French, and German. And then we also have 4 underrepresented languages, which are Swahili, Bengali, Telugu, and Thai. So for English, it's around 60, but the sort of surprising thing is it's actually doing really well on languages like Bengali and Telugu that are sort of only like this very small proportion of the training data. And the second paper is about using chain of thought to solve tasks in Big Bench. Big Bench is sort of this crowdsource benchmark of around 200 different NLP or text tasks. And some of the tasks are like pretty challenging. So on the left, here's one such task. Basically, it's a state tracking task. So I omitted the few-shot exemplar, but the question is basically, if you follow these instructions, do you return to the starting point? Turn left, turn right, take 5 steps, take 4 steps, turn around, take 9 steps, and then the model has to answer the question. So you can imagine the model will struggle if you just ask it to do this directly. But if we use chain of thought prompting, it turns out the language model can do these quite well. So here's an example of the chain of thought produced by the model. So basically, you can see it state tracks at every single step, and then it gives the final answer. And this is basically like, we give chains of thought like this to the model, and then it generalizes to new questions. In this paper, we studied 23 such challenging tasks. And on the left, we can see that with standard prompting without chain of thought, models are worse than average human raters on most of the tasks. That's the red bars. And then on the right, when we do chain of thought prompting, the model is doing as well as the human rater on 17 of the 23 tasks. Great. So I also wanted to just spend a minute talking about a look forward in NLP and large language models. And let me just clarify that these are just my personal interests, and they don't represent sort of what everyone on the field is working on. So I think continuing scaling is a really important research area, given that we've seen such strong results and new capabilities from scaling large language models. I think it seems like a promising direction to continue scaling. I think right now there's been a lot of recent work on how to best prompt language models, but we're still only at the the tip of the iceberg for how much we know about the best possible abilities of language models and how to use them in the best way. I think there's a lot of applied work with language models that are out there. For example, you could potentially use language models to help train therapists to help in creative writing and maybe even to help with scientific like science research. I think benchmarks are also a really important direction recently, because we've sort of seen that like a lot of benchmarks will saturate very soon after they're created. And I think creating challenging benchmarks that sort of evaluate the limits of what models today are capable of is a really important endeavor that will help us characterize how good these language models really are at these tasks. And then finally, I think compute efficient methods for improving language models are also important, given the fact that there are sort of hardware and other constraints on just simply scaling the language models. If there are ways to improve, say, the data or the architecture or the pre-training objective of language models that can improve their performance without having to increase the scale, I think that's a really important research direction. Great. Yeah. Thanks for listening, and I'll take questions here. Feel free to email me with any feedback, and our team is also hiring interns. So if you're interested in that, I'm happy to correspond over email about that.
When was this released?
This was approximately 3 to 4 months ago, I believe.
Oh shoot! Okay, it's too late.
Yeah. Well, who knows? There's a little bit of flux as to what's going on over at Google these days, right? So
fair enough. I will. Hey, what's the worst that can happen? You can say no.
Right. They could say no. I mean, one of my students that I tutor for this project at Caltech that we do, just like last week got his internship with some sort of, they couldn't even tell me what they did. They just wanted to know about him. So I don't know what he's getting himself into, but he got his internship. So,
Oh, cool.
Yeah, it doesn't hurt to ask.
Yep.
Yeah. Anyway, comments, thoughts from everybody? Let me stop the recording right now.